All right, this is part 3 of 5 of the semester 1 final exam review. Number 24 is all about finding the average atomic mass. So what this is telling you is a certain percentage of the time an atom weighs 38.99 AMU, and the other percentage of the time it weighs a different mass number. So you're supposed to figure out the average atomic mass. So that's like saying that 60% of the time you weigh 100 pounds, making a random example, and 40% of the time you weigh 120 pounds. So if I asked you the average weight, a lot of people would just go in the middle and they would say 110. But that's not right, because slightly more of the time you weigh 100% or 100 pounds. So what you do is you move the decimal 2 back from 60. So 0.6 times 100 is 60 pounds. Plus, you do the other one, move the decimal 2 back, 0.4 times 120, and that is 48 pounds. Add those together. The average is 108 pounds, which makes sense that it's a little bit closer to 100 than being right in the middle at 110, because again, 60% of the time you weigh 100. So that's exactly what this problem is, only it's got, decimals and things, but don't let that mess with you. So you move the decimal 2 back, so this is 0.6075 times kind of like the 100 pounds, but the 38.99, plus, then move the decimal 2 back on the other relative abundance, multiply it by the average weight for that isotope, and then add it together and think about your answer, make sure it makes sense. So for this one, it's between about 39 and 41, but most of the time it's closer to 39. So it makes sense that it's not right in the middle at 38. What is an isotope? So remember that atoms can have different numbers of neutrons. If there's a carbon atom, it always has 6 protons. But it can have 2 extra neutrons. So for example, this carbon that I wrote here has a mass of 12 because the protons plus the neutrons make the mass number. And when you're writing a generic isotope notation format for an atom, you always write the mass number in the upper left corner and the atomic number in the lower left. And you can always do the mass number minus the atomic number, and that will give you the number of neutrons every time. That works. So number 26 is asking you to write out some isotope symbols. So you add 12 plus 14 to get that mass number that goes in the upper left corner, and protons is equal to the atomic number. Then you go to your periodic table and you say, okay, what element is number 12? This question is asking about magnesium. In a similar fashion here, this one gives you the mass and the neutrons, so it's a little bit trickier because it wants you to do a subtraction to figure out how many protons and the identity of the element. And then you go to your periodic table and say, okay, number 29 is copper. Number 27, explain the difference between core electrons and valence electrons. So let's look down to number 28 because I already have a picture drawn here. The valence electrons are just the electrons in the outermost shell. And we've been talking a lot about those lately because those are the ones that are available in that outer shell for bonding. And then the core electrons are everything else inside. So sometimes you have to add them together. So for this particular atom, there are 10 core electrons and 2 valence electrons. So let's look what it's asking for here. It says nickel, and it just told you that it has 2 valence electrons. So you have to go to your periodic table, find nickel, and say, okay, nickel's number 28. So that means it has 28 total electrons. Since there are 2 in the outer shell, I need to subtract to figure out how many are left in the core, which makes sense, 26. Calcium is a little trickier in a way here because it didn't just tell us the number of valence electrons, because calcium is in not a weird spot like the transition metals. So because calcium is in group 2A, that means it has 2 valence electrons. And since it's number 20, it's got 20 total. So we can just do 20 minus 2 to get how many are left in the core, 18. For number 28, it says, what if you need to draw a detailed picture of a magnesium, for example? Magnesium is in period 3, group 2A. So that tells us some things. Also, it's number 12. So let's start there. Because it's number 12, we know it has 12 protons in its nucleus. We also know that it has 12 electrons, assuming that it's neutral, which you should, unless someone tells you differently. So we're going to need to put 12 electrons somewhere, and the 3 from the period number tells us that there's 3 shells. So I started by drawing the 3 shells and automatically putting a 2 in the outermost shell. 12 electrons minus 2 in the outer shell leaves 10 in the core. And you kind of have to remember that the inner shell always has a max of 2 electrons, and then that second shell always has a max of 8 electrons, which makes this work, because when I add those 3 together, I see, okay, it's got 12 total electrons. What about the neutrons? So the average atomic mass is the bottom number on the squares on the periodic table. If I round that to the nearest whole number, that will tell me the most popular number of neutrons that a magnesium has. So 24.31 rounds to 24. So I do 24 minus the 12 protons, and I get 12 neutrons. So that's the other piece that I needed for my picture. What's the difference between a ground state electron and an excited state? So this came up a lot when we were talking about the flame tests. A ground state electron means it's very stable, and a lot of times it means it's closer to the nucleus. But when they get excited, they jump up to a higher shell. But that's unstable. What goes up must come down. So when they fall back down, they release a photon of light. They can also release things that we can't see, like infrared, ultraviolet, things like that. But a lot of times when we were doing things like the flame test, it's a lot more fun to use elements where we'll get to see some of the cool results of those jumping electrons. So a bright line spectra is when we were using the spectroscopes and we were aiming that little slit with a diffraction grating, and we were seeing all these different bands that were different colors. So every single element has a unique bright line spectra. It's like the fingerprint. And each of these bands is coming from an electron that's jumping up and falling back down. Because every single atom has a unique number of electrons and how many shells are filled, and depending on how many protons, the shells might be held more closely or they might be further apart. There are different distances between the shells. So I was trying to draw that one a little bit smaller. So that results in different colors overall. And that diffraction grating in the spectroscope is a tool that splits the net result, which is the color that we see, because our eyes aren't detecting these individual bands. Also, it's important to note that if it's a high energy color, that comes from an electron that's been making a big jump and falling back down, versus a smaller jump would result in a lower energy color like red. Because if you see the wavelengths drawn, red wavelengths will be longer versus like blue, for example, or violet will have a higher frequency, shorter wavelength. how come when we had, for example, helium gas, we were looking at it through the spectroscope, why did we see so many different colors of light? Because helium only has 2 electrons. Well, there were so many millions, billions, trillions of helium atoms in that gas chamber that when we turn on the electricity, they don't always make the same jumps depending on how much energy that electron absorbs. And even though there aren't electrons in these shells when the atom's in its ground state, there are an infinite number of shells. So these electrons can be making jumps, maybe not falling all the way back down, and maybe it makes another jump and falls back down. So you're going to see the result of all of those electrons jumping, and that's why you see so many different bands of light. All right, fission versus fusion. So usually fission is a big, heavy atom, and you bombard it with something, and then it splits. And in that process, it releases a lot of energy, because remember, there's so much energy holding that nucleus together that when it's not needed anymore, and it's split into smaller new nuclei, that energy goes somewhere. So fission is all about splitting. Fusion is when 2, usually smaller nuclei come together and form a larger nucleus. That also results in a release of energy. So that's happening in the sun and stars. That's a natural process. We can also make a fusion bomb as well. And then back to fission, this is what they do in power plants to heat water, which turns into steam, which spins a turbine, which generates electricity to power our homes and schools and ultimately your cell phone. So pretty cool that that's what's going on. We don't really think about it. Alpha and beta, more nuclear changes that can happen. This is talking about radiation. Radiation is when an atom naturally is decaying. It's falling apart, releasing small particles and energy. A lot of times you do not want to be around that. But there are some good uses too, like medical uses. So an alpha particle has a positive charge, and it's made of 2 protons and 2 neutrons. So it makes sense that it has a positive charge because protons are positive. So when something loses an alpha particle, because it had 2 protons, that's the atomic number. The atomic number goes down by 2. And because it's made of 2 protons and 2 neutrons and weighs 4, the mass goes down by 4. Okay, so in alpha decay, you're starting with a big, heavy nucleus, and a chunk of it, like maybe that part of it, actually just goes away. In beta decay, it's a lot different because the mass isn't changing. I'm going to go off to the side. In beta decay, you've got a nucleus, and a neutron can be thought of as a positive and a negative, and overall it's got a 0 charge. But in beta decay, this part leaves. So a neutron changes into a proton. That's interesting because the atomic number then, there's an extra proton, so it goes up by 1. But the mass doesn't change because neutrons and protons have the same mass. Number 34 wants us to identify what kind of decay is happening. So here we see that the mass, it was 222, and now it's only 218. The mass went down by 4. The atomic number went down by 2. Automatically, that means it's alpha. Okay, going back to these numbers, it matches those. What about letter B? Carbon 14, when you see an atom dash and then the number, that number is its mass. So if it goes from carbon 14 to nitrogen 14, the mass is staying the same. And carbon is number 6, nitrogen is number 7. So the number of protons went up by 1. So that must be a beta decay. lead changing into mercury, we need to look at a periodic table to figure out a little bit more of what's going on. Oops, I'm gonna erase some stuff here so we can see. All right, so we're going from lead to mercury. Lead is 82, mercury is 80. That means the atomic number is going down by 2. So automatically we know that that's alpha decay. And then the last one, look, the mass is not changing. 228 to 228. 90 is going up by 1. So that must be a beta decay. Number 35 wants you to refer to your band of stability. So let's go to our semester 1 exam equations. I want to remind you about this, that it's number of protons on the bottom, number of neutrons on the side, and you basically just graph how many protons and neutrons there are in your atom, and if it falls in the center of the band, then it's something that's stable. If it's something on the edge, then it's probably radioactive and unstable. Okay, and if it's out here, it probably can't exist for very long, if not at all. So the first question was, as you increase the size of the atom, what happens to how many neutrons are needed compared to the protons? And you can see at first it starts out like 20 protons, 20 neutrons. And as you get larger and larger, 80 protons, you need way more than 80 neutrons. Neutrons are like the glue that hold the nucleus together. So the number of neutrons needs to increase as the atoms get larger. What if an atom has 80 neutrons? How many protons might it have? 80 neutrons. Let's go over to here. Right in the center is number 60. So you would need, what did I say in my answer key? Somewhere between 54 and 67. Okay, so I just gave a range there. That's really specific, and if you don't get the exact same as me, that's totally fine. And then what elements could that be? Well, I must have just looked up element number 57, which is down here. And was it element number 57? 54, sorry, through 67. Oops, I want to go to my periodic table. So number 54 is Xe, and so I just gave a range here all the way through HO. Okay, again, it's not important that you matched my specifics here as long as you understand how the chart works. Would an atom with 90 neutrons and 90 protons be stable? Okay, 90 protons, 90 neutrons. Let's graph it out. Heck no, that's not even close to being on that band of stability right there. How do you determine if something is radioactive? Like we talked about, if it's on the edge of the band, but also if it has more than 83 protons, it's typically radioactive. So larger atoms are more unstable, or they have isotopes that can be unstable. And again, radioactive is when the nucleus is spontaneously falling apart, releasing energy and small particles, or even both. Knowing how to write out a nuclear equation is important too. So as long as you remember the patterns of the alpha and the beta particles, you're good. So polonium-208, you look up the number of polonium on the periodic table, and remember the atomic number goes in the lower left and the mass goes in the upper left. And then you subtract because a chunk of it is falling off. So you do 208 minus 4 and 84 minus 2, and you get 204 and 82. Then you go to your periodic table and you say, what element is it now? Number 82 is lead, so Pb. Beta decay. Sodium is number 11. You look that up on your periodic table. Again, the mass goes in the upper left corner. If it's a beta decay, that means the mass stays the same, but the number of protons goes up by 1. So now, number 12, it's changed into magnesium. Fusion are really different kinds of reaction because the plus is before the arrow, because two small nuclei are adding together to become a big one. This should be Mg. It got cut off there. So 4 plus 20 makes 24. 2 plus 10 makes 12. That's a new element that formed. And that is it for this